Hello everyone, today we are going to present our DIY celestial sphere model. So basically, this model represents the sky as an imaginary sphere surrounding the Earth, with the observer located at the center. Using this model, we are going to explain the celestial equator, the ecliptics, and also the apparent motion of the Sun during different seasons. Starting from the celestial equator. Its definition is the projection of Earth equator onto the celestial sphere. So basically, it divides the sky into the northern and the southern celestial hemispheres. So in the model, it is the blue star at the center of the globes, the outer globes, and also you can clearly see that it is the projection of the red line, which is the Earth equators in our model. Next, for the ecliptic. The ecliptic is the apparent path of the Sun on the celestial sphere over 1 year. So we represent the ecliptic as the green stripes in our model. Now that we understand the celestial equator and the ecliptic, we can explain how the Sun's position changes throughout the years. This leads to the equinoxes and solstices, which determine seasonal changes in daytime and nighttime. As the Sun moves along the ecliptic throughout the years, its position relative to the celestial equator changes. This creates four key seasonal points: the two equinoxes and the two solstices, which are vernal equinox, summer solstice, autumnal equinox, and winter solstice. So you can compare between the model and the visualizations. Starting from summer solstice. So, summer solstice in this model is the place that the sun at the positive declinations at around 23.5. So, I will mark the sun as the icon of the sun in the model. Next, as you know that green stripes is the ecliptic, right? And I would like you to keep a close eye on the axis, whether it is like north or east or west. So as you can see throughout the models, as the earth revolves around the sun, we can see that the sun tends to rise at the northeast and then sets as the northwest. So we can combine and also visualize according to the observer point of view like this pictures. Yes, so as you can see from the model that the sun rise from northeast, right, and sets at northwest, so we can clearly see that the daytime period tend to be longer than the nighttime period, which is the important characteristic of winter solstice. Moving on to winter solstice, I would like you to continue observe the way of the sun icon relative to the plane of the observer. So as you can see that the sun rises from the southeast and sets to the southwest, and we can visualize in the observer point of view as these pictures. So you can see that winter solstice tend to have like less time in the day period compared to other days, which are summer solstice and equinoxes. So it leads to our conclusion that winter solstice has a spatial characteristic of the longer nighttime compared to the daytime and also compared to other days. Lastly, I would like to talk about the equinoxes, starting from vernal equinox. So, according to the model, we can see that the sun rises at precisely 8 and sets at west. So, as it is the same thing with the autumnal equinox, which is the sun rise at the east and also set at the west. So using this model, and we visualize it into these pictures of observer point of view. The time of the day, the period of the daytime and the nighttime are equal. So this is the main characteristic of both equinoxes, vernal equinox and autumnal equinox.
Now let's talk about the equatorial coordinate system, which is used to locate celestial objects on the celestial spheres. The reference plane of this coordinate system is the celestial equator, and the reference points of this coordinate system is the north celestial pole and the south celestial pole. In these coordinate systems, there are two types of coordinates, the declination and the right ascension. The declination is measured either northward or southward with respect to the celestial equator, and the right ascension is measured along the celestial equator. The declination ranges from positive 90 degrees at the north celestial pole to negative 90 degrees at the south celestial pole, while in the right ascension, it ranges from 0 hours to 24 hours. So next, I'm going to talk about how we can identify the declination of the celestial objects from an observer's point of view using the horizontal coordinate system. So first, we will have to determine whether the observer is in the northern hemisphere or the southern hemisphere. In this case, or in this model, the observer is located at the northern hemisphere, so therefore we have to locate the north celestial pole, which can be located by finding the observer's latitude. In this case, the observer's latitude is at 30 degrees. Therefore, using angle chasing, we can deduce that the northern celestial pole is measured 30 degrees from the horizontal plane. And after that, we know that the celestial equator is perpendicular to the direction of the north celestial pole. So we can draw the celestial equator perpendicular to the pole, and then we can locate the declination of the stars by measuring with respect to the celestial equator. For example, a star right here measured around 30 degrees from the celestial equator northward. So therefore, this star right here has the declination of around positive 30 degrees, while this star right here is located on around 45 degrees down below the celestial equator, or in the southward direction. Therefore, this star right here has the declination of negative 45 degrees. Finally, I will explain about how to identify circumpolar stars using declination. So a star is said to be circumpolar if it never rise or set, but instead circled around the celestial pole and stay above the horizon all the time. For a star to be circumpolar, its declination should be sufficiently large for the observers in the northern hemisphere, but should be sufficiently small for the observers in the southern hemisphere. In particular, its declination must be at least 90 degrees minus the observer's latitude for the observers in the northern hemisphere, while it should be at most observer's latitude minus 90 degrees for the southern hemisphere. For example, this yellow guy is located in the latitude of 30 degrees. So therefore, for a star to be circumpolar, its declination should be at least 90 degrees minus 30 degrees, which is 60 degrees. And and suppose if suppose for an observers in the southern hemisphere with latitude of 22.5 degrees, for a star to be circumpolar, its declination should be at most 22.5 minus 90 degrees, which is negative 67.5 degrees. And I think that wraps up the presentation. Thank you for listening.